Beta-keto esters, whose structure is shown here, are actually acidic at the methylene position flanked by the two carbonyl groups. Specifically, we talk about that position. This methylene position is actually acidic. That's because the conjugate base, which is the enolate or the alpha carbanion, is stabilized by resonance. The pKa here is actually about 11 at the methylene position, that position, the methylene position flanked by the two carbonyl groups. A suitable base or a base of a suitable strength can actually selectively deprotonate that position. Here we talk about alkoxides, for example. So if beta-keto esters are treated with an alkoxide, then the alkoxide will deprotonate the methylene position here, the position flanked by the two carbonyl groups, to give the corresponding enolate. Once that enolate is formed, then its reactivity or chemistry can be utilized by reacting it, for example, with an alkyl halide. So let's show that. If this beta-keto ester is treated first with, say, sodium ethoxide, if it reacts with that beta-keto ester, it should give the corresponding enolate, the enolate at the alpha position, at this position flanked by the two carbonyl groups. If that enolate is then reacted with an alkyl halide in a subsequent step, then substitution reaction should take place. So that's if the enolate reacts, let's say, with RCH2X, a primary alkyl halide, then a product of this type should be obtained. This substitution product, where the alpha position has been alkylated, that's after the enolate formation, which was followed by the enolate alkylation in step number 2 with this alkyl halide. So a product of this type should be obtained. Now, if this product is treated with an acid in the presence of heat, let's see what we should write or what we can predict. Of course, the acid or the ester in the presence of an acid and heat, the ester should undergo hydrolysis. So if this product is treated, let's say, with H3O plus and heat, the acid should affect hydrolysis of the ester, so the corresponding carboxylic acid should be obtained along with the ketone. But the reaction will not stop there. The reaction will actually continue for that carboxylic acid intermediate product, if you like, to lose carbon dioxide, in fact, effectively overall, to lose the carboxyl unit, if you like, in what's called decarboxylation reaction. So the final product is actually a ketone without the ester or without the carboxylic acid. So this is the product. Please note that carbon is that carbon, so we can actually show this with alpha, for example, if we begin with alpha here. So this is the alpha position or the alpha carbon, that's the alpha carbon. Obviously, the CH2R comes from the alkyl halide. So again, if this alkylated product is treated with an acid in the presence of heat, the ester should undergo hydrolysis to give the corresponding carboxylic acid, and the carboxylic acid will be lost in the form of carbon dioxide to give the final ketone product. Let's write that carboxylic acid intermediate product to see how this decarboxylation reaction takes place. This is the carboxylic acid that should be obtained after treatment of that ester with an acid in the presence of heat. We can actually redraw this carboxylic acid like this. Of course, we have not changed the structure, it's just we have drawn it slightly differently from the way it's drawn here. Now, this carboxylic acid will then undergo decarboxylation. Let's see how that takes place. We can move or push electrons, if you like, from this carbon-oxygen double bond. So a bond between oxygen and hydrogen forms as a result of breakage of that pi bond between carbon and oxygen. The hydrogen-oxygen bond then breaks, and a double bond is formed here between oxygen and carbon. And obviously this carbon-carbon bond breaks, and if it breaks, it forms, or a double bond is formed between these two carbons. So let's write the products that are obtained now. So of course oxygen has been bonded with hydrogen, so there is OH here, and a double bond between these two carbons, so a carbon-carbon double bond. And of course we have CH2R, and here there is a double bond between oxygen and carbon, so we have oxygen, we have carbon, and of course that carbon, and a double bond between carbon and oxygen. And if you look at that structure, you can tell very easily and very distinctly that that's actually carbon dioxide. So that's how this carboxylic acid unit is actually lost. It is lost in the form of carbon dioxide. So this is CO2. Now, if you look at this intermediate structure, or this intermediate product, you can also tell it's actually an enol intermediate. This is an enol. But enols, if you recall, undergo tautomerism to the ketone form. So in what's called Keto-Enol Tautomerism. So this enol should tautomerize to the final ketone product to give the ketone. So this is Keto-Enol Tautomerism. The enol, once it's formed, it should undergo tautomerism to give the final ketone product. So this is tautomerism, or Keto-Enol tautomerism. So this is how this carboxylic acid is lost upon heating it after its formation with the treatment of, or after the treatment of the ester with an acid. The carboxylic acid, once it's heated, it should be lost in the form of carbon dioxide, as clearly shown here. Of course, the presence of that ketone is essential. The two carbonyl groups, of course, have to be in a 1,3 carbon relationship, if you like. So this beta keto ester is characteristically very, very essential for this decarboxylation. The ester has to be, if you like, and the ketone, of course, they have to be in a 1,3 carbon relationship for the ester. Once it's transformed to the carboxylic acid to be lost in the form of carbon dioxide. This reaction is called decarboxylation because the carboxylic acid is lost. So this is decarboxylation. And this reaction should be a very useful reaction because we start with a beta keto ester, and enolate is formed, subsequent alkylation of the enolate to give a product of this type, and then heat followed by an acid with heat should hydrolyze the ester, but of course that will be followed by concomitant decarboxylation of the carboxylic acid in the form of carbon dioxide. The final product is a ketone which is alkylated, or where the chain is elongated. So this should be a very useful reaction where the carbon chain has been elongated, and of course the ester is lost in the form of carbon dioxide.